Okay, as I was saying, softer before, louder now. The subject of this talk is secure multi-party function evaluation. I will present to you a series of algorithms, which are all variations of a common one called Oblivious Transfer. We are first going to see what could be called a toy example, which is an algorithm that's simpler. We'll use it as an example to try to understand some of the fundamental concepts in cryptography we will care about when analyzing the one that's not a toy example. And my intention is to also use some superficial applications of some cryptographical techniques that you will probably be learning in depth sooner. These algorithms will allow several agents to interact together. We'll see examples in a second, but the idea is you own some inputs which are private, and you want to evaluate a function together without sharing the private data, neither between each other, neither with a third party. The way most of that happens on Web 2 is you delegate it on a big company such as Amazon, and you ask them pretty please not to spy on you. That's what we want to avoid in this case, and we will be able to prove our algorithms do not leak information. Thanks a lot. One example that you can review is a project called TLS Notary. The algorithms we are gonna use today are typically fairly asymmetrical. Asymmetrical in the sense that there's typically one party that will obtain no benefit and no increase in their known information when the process ends. Notary leverages this kind of algorithm to deploy a server which is called a notary. If you've read the open source code and the algorithms, you can be sure that that server gets no information from you, but it still allows you to guarantee third parties that your TLS communications follow a certain pattern. The way it does it is you, together with the notary, create a shared TLS signature when doing communications with Web 2 servers. And it's quite a complex project. I started to create this talk with a paper they published explaining their technical requisites. But that paper is like 50 pages long, and it doesn't have many of the primitives you need. You can reach as short as 50 pages if you already know how most of these work. What I did is I compiled everything from scratch, all the sources, and that's what we're gonna see today. But we'll start with an example which is not from TLS Notary, and it is called Benaloh's algorithm. We'll start with this problem. Yes?
This NPC TLS is the key exchange, right?
Yeah, what you do in TLS Notary is it's a mediator in your TLS key exchange. Instead of creating the key as it's typically done, you'll both provide inputs to a shared key. That's what we'll learn to do today. That's the final thing we are going to obtain from this series of algorithms today. But we'll start with one that's not related to it, just to see some topics in how you research cryptographical algorithms for multi-party computation, the notation, etc. In this case, we have three characters, which are called Alicia, Bernardo, and Carla. They are committing money to a common initiative, and they want to know what's the available total without revealing how much money was contributed by any individual member. This is what we'll do first with our first algorithm. My memes won't be seen with this slide, so let's skip this. And we'll start with some definitions and formalizations. In this case, we've got three users. Each one of them owns an input, which is the amount of money they are committing to the project. So that's gonna be 3 x values, x1, 2, and 3. That's the first line there. And we have an objective function we want to evaluate in a safe, private way called fa. In this case, it's the sum of the three values, x1, x2, x3. That's the only detail, the only extra detail any party will know once the evaluation is finished. So we see in this example already, we can define secure function evaluation. It's multi-party in the sense that there's users, there's a set of users who are involved, and every user knows their private input or private inputs. In this case, I added there that the inputs are binary numbers. We'll typically rely on that, but of course any finite number can be expressed this way. That's when you see this notation, what we say is, it's n iterations either of 0 or 1. There's a function we want to evaluate, or several sometimes, different functions if it's asymmetrical. And it's gonna take the private inputs and their security. At the end of the evaluation, no user j can know any xy if y is different to j. Those are the formalizations of this. We can also define an honest but curious adversary. This has several names in literature. This is one that's descriptive enough, in my opinion. So what we are saying with this is we are not going to be extremely careful about the demonstrations because it will be too long a talk and too technical. But we will have in mind that in this case, the kind of adversary we imagine strictly follows the protocol, which is reasonable for the notary because it's going to be a piece of open source code which is deployed. So you can know every procedure it's following. And so what this implies is they are not breaking the rules, let's say. What this adversary does is it will try to get as much information as possible from the inputs they accumulate during the execution of the protocol, which is called the trace typically, but they won't do anything else. That's the honest but curious. They won't trick the algorithm, but they will try to use their exposed information as much as possible. In this case, in the algorithm I'm showing to you, there's already a vulnerability that the honest but curious adversary can exploit. Maybe somebody already saw it, but if we are evaluating, I want to go back, give me 1 second. It seems like the arrow is, okay, it's back. Great. As you can see, there's a limit to how private this function can be. Since it's the sum of three numbers, if two parties collude, that is, they are allied to extract data from another party, they can immediately do it. They can just follow the protocol, get their outputs, and then share their inputs. So if I'm x1 and one of you is x2, and we want to know how many would a third person commit to a project, we do this, and then in the end, we use our private inputs, we subtract them from the total, and we learn the value of x3. So this is, at most, invulnerable to one-party collusion. So if two of the members work together, they will steal the information of the third. What we want to prove is that if that doesn't happen, this works. So let's propose an example, an algorithm, sorry. This is T-privacy, the thing I've just mentioned, again, that we want to measure how many users need to collude in order to defeat the security. This is the proposed algorithm, Benaloh's algorithm. Every user will send two blinding random values to their peers. So there's going to be 6 random numbers shared across the users. Every user will commit their private data blinded by adding 2 random values, one obtained from every peer. The commitments will be used to obtain this function we want to evaluate by every peer. Let's look at a trace of the algorithm, which I prepared. It's the file called 01 algo Benaloh. This is a format we'll use for every algorithm we are considering today. This is the only one in which there's 3 users. That's a little inconvenient, so we'll add an improvement later when it's only 2. There's first a setup. In the setup, we can see that every user prepares their own stuff. I forgot to add the fact that they store their private input. That could be before or in the setup. So user 1 stores x1 for themselves in their private registry, and the same with users 2 and 3. And each one of them obtains via a random algorithm 2 numbers, not factors in this case, that we'll call blinding elements, right? What they will do next is they will exchange them in a strategical way, which is every user provides 2 different blinding factors from... What, sorry?
That's not in the slides?
No, it's a separate file also in the same download I sent to you. Yeah, it's in Wormhole.
It's a zip.
It's a zip file, and this is the 01. They are numbered by the, the order I plan to follow. So they exchange the blinding values. These are like the inputs, new inputs they need for the exchange. And what they'll do is each one of them will create an auxiliary intermediate value. They are all the same, so let's look at one. This is what user 1 will do. What he'll do is he'll hide his value using a lot of blinding values, the 2 he created plus the ones that come from the other users. What this ensures is, we'll look into this in a little more detail in a second, but you can already tell that the result, right, will make it impossible to learn the value of x1. Why? Because it's enough that one of the parties created an actual random number, right? Because all of them are participating here. These are blinding factors from the first user, the second, and the third. So if only one of them was honest and created actual random values, it's impossible to extract x1, the first private input, from y1. And the same happens with all of the users, right? They all create their commitments this way, right? This is a commitment because they are going to share it across with all the other users. This is not directed. So everybody sends their results to everybody. That's what these arrows are, right? From every user, their value goes to all the others. And that's it, right? Now, if they add all of the values together, if they add a y1, y2 plus y3, all the blinding factors will cancel. Why? Because every blind factor is twice in this sum. If we look at how the y's are defined, let's look at 1, for example, right? These 2 are here and here. Minus R1, minus S1. And if we add the 3 y's, right? Here I'm canceling it, the R1, and here I'm canceling S1. And this will happen with all of them, right? So if I add y1 plus y2 plus y3, I am getting actually the value I wanted, fa, which is x1 plus x2 plus x3. That's how the algorithm works. That's it. We've privately and securely evaluated the function. And we'll look in a second about how we can prove it, but that's how it works. Does anybody have any question this far?
So you give R to others?
Sorry?
You give your R to other two?
Yes. Later, whenever you want, you can look at this. I guess this is good enough. Like, you can see what's being exchanged here. Like, you can see, like, user 1 sent one of his blinding values, R1, to user 2, and another S1 to user 3. Every user sends one blinding element to the other 2, different elements, right? So that's why we know it works, because every commitment, every Y element is obtained by mixing a private input from a user and the random blinding values created by the 3 of them. Again, with only one of them being honest, we know it's hidden, right? And that gets us to the latest thing I wanted to show with this simple example, which is, how can I know this is sure? That's a huge topic to begin with, because we are not looking at one of the possibilities, which is malicious adversaries with, somebody could like have a Trojan in your machine, right? We are not analyzing that. It's an important topic. But our opponents are only honest but curious. Why? Because we don't want to do a ton of maths, and because on Friday you'll see a more sophisticated version of this, I believe. So what we'll do when we want to learn if an algorithm works is simulating it. What's a simulation? Let me go back to my notes. So back to the main track of notes. A simulation, and we'll only see the intuitions of this, but I have material about that if you want to see it in another session too, is we'll create a hypothetical trace. Again, a trace is, sorry, I haven't shown that. Oh, it's here, yeah. A trace is this. What's this? This is the trace for user 1, is the collection of every element of information he had access to. Some are his private elements, some are his public elements, and some are public elements from the other, public or semi-public, like these R's, right, which weren't shared with everybody. So this is everything I've seen during the execution. What I can do is I can, to evaluate security, is I can create a fake trace in which every private input is random, right? So I know it's noise because I'm creating it. And I'll theoretically compare them. This is not a simulation in the sense like in statistics, bootstrap, for example, when I repeat an operation a lot of times and I try to obtain a convergence in the statistics. It's not that. The simulation in this situation is I replace the information with randomness and compare, theoretically, right? And what we'll see in this case is if we, let's say, user 1 wants to recover the private input of user 2, x2, and he's alone. Again, if he has help from user 3, that's trivial. They can do it with the result of the function they've evaluated. If that's not the case, he'll need to do this kind of calculation, right? He'll do x1 is y2 plus r2 plus s2 minus r1 minus s3. And if you go look into the trace, which again, I share this note with you, you don't need to do it now, but you will see that the only thing he's missing is S3. So in the end, what he wants is to evaluate a function, that's the point 3 here, which is a function of the trace and S3. He's missing S3, so what we are asking ourselves now is, what does he need to do in order to get it? But S3 is a random value that hasn't been shared with them. So what he's facing is the chance of guessing a random value, which is the same as in the simulation. Therefore, this is semantically secure. In what sense? Again, he's honest but curious. He tried to extract data that's not meant to be shared. And if he wants to do it, he'll need to guess something that's noise, which is impossible, basically, right? So that's how we can, again, this is the intuition of a simulation. We could do it, this can be modeled mathematically with probability, and it's not that hard, but it's the topic of another session, and it's a long topic. We'll do it this way. We'll only look at the intuitions for this. We'll start with Oblivious Transfer now. Does anybody have any question about what we've discussed this far? Yes? Well, yeah, if you, for example, in this simulation, what happens is, if you were to do a Monte Carlo simulation and to compare your whatever strategy you have, which is honest but curious, with, and you search for the distribution of your parameters, you'll find your chance of finding the actual value of x2 is 0 if you Monte Carlo simulate it. It's the same as in noise. If the set is very small, let's say we are only working with 10 numbers, or let's say we want to guess like, I don't know, the ID number of a person in a country. Argentina has less than 50 million inhabitants, or slightly more, let's say. For a computer, it's a small number. You can try, right? And you eventually will find it. But the probabilities of doing, with any strategy you imagine, consuming this data versus brute force are the same. 1 in 50 million, right? That's it. That's how the simulation works. If you were to do Monte Carlo, you should find, again, that it is distributed the same way as some random noisy function. As close to white noise as you could wish. That's the definition. So again, the algorithm is 1 secure. With 2, this analysis makes no sense. Now let's look at Oblivious Transfer. This is the main algorithm I want to discuss with you. We'll then see improvements on it. But this is the most interesting one, and the one we use as a building block later. So This is a typical notation. Also, during these slides, I try to keep a consistent notation, but I also try to sometimes use several, because if you are interested in the topic, you'll find it's highly fragmented across articles and papers. You need to go hunt for your stuff, and everything has different names, different notations, slightly different assumptions, which is how it works with reasonably new topics, right? This is a typical notation for Oblivious Transfer. We'll call it 1 out of 2 Oblivious Transfer. This is the only one we are going to use, but it's fairly easy to extend. And the idea is this. It's a process in which, we'll always analyze the algorithms in the terms of what are the private inputs of all the agents and what they are intended to obtain in the end. That's what I'm listing here and what I look for each one of them, as we did with the past one. In this case, there's a client and a server, let's say. The client knows a choosing bit, which is only one bit, 0 or 1. That's a private input for them. The server knows 2 messages, M0 and M1. These are arbitrary elements of arbitrary sets. For example, it could be strings. What's going to happen is the client will input his bit B into the securely evaluated function and will know one of the messages. Which one? The one that's indexed by B. MB is either M1 or M0, which are here. So what I'm meaning with MB is that I'm taking one of these elements. And an interesting detail is the server learns nothing. That's the notation for an empty output for the server, at least in some of the articles. So the server inputs 2 messages and gets nothing. This is a highly asymmetrical algorithm, which is an advantage in occasions. For example, for this project, TLS Notary, the notary is a server, again, that has no real secrets. It has no interest in the operation and will reveal its inputs in the end. Why? Because, why can I do this? Because of this asymmetricality, right? If I had to store secrets in it, if I needed it by design, it would be way harder to do it in an altruistic way, because it would require way more computing power and protections and stuff. So you might be wondering, this happened to me at least, how useful can that be? Because it sounds very particular. Why do I care about this? But in the end, it has a ton of applications. We'll see 3 today. One first, and I believe this was the first application that was created for this, is what's called private, it's PER, private information retrieval, right? There could be a huge data, or not huge, but there could be a database that only contains encoded messages and knows nothing about them, but they are stored there. And users would, using not 1 out of 2, right? 1 out of many as elements in the database. For example, you could do this many times with a binary tree and cover an arbitrary number of elements, right? And this database would deliver data to me, but it would not know what it has delivered to me, which is of great usefulness, because otherwise it could do a statistical analysis and start checking which users retrieve which data and learn stuff about them, as it's done like in Facebook even. So that won't happen here because they don't know what I have retrieved. So at the beginning of the process, the server knows 2 messages. The client wants 1 of them, and the protocol is highly asymmetric. This, I already said it, sorry for being repetitive. So it's basically this, right? It's the matrix. We'll discuss these 4 intuitions and look at the, again, at the schema of this algorithm in a second. So it relies on public keys. Both parties will exchange data that is useful to build 2 private keys. And what this algorithm will ensure is that only one of them is legit and the other is noisy. So one is useful to decode data and the other is not useful to decode any data. What the client will do is they have agency on which key is which, if the 0 or the 1. And that's what's going to determine what he obtains at the end of the process. The server encodes both messages with 2 keys that the server can't understand, so the server doesn't know which one you've chosen, and they deliver both messages to you, and you will only be able to decrypt 1. That's how it works. Let's look at... No, I'm pretty bad at this. Okay, I'm getting better, I guess. Let me zoom it. Okay. So there's way more stuff happening here, but this is the most complex one. Then this is going to be a building block. What's happening here? This is what I repeated in different ways during the last 10 minutes, right? In the setup, also I changed this plot a little. Now we have 2 lines for every member of the transaction. So the client and client secrets are 1, and the server and server secrets are 1. I did this so we can distinguish when something's stored privately and when something's shared across the parties more easily. In this case, there's the stuff I mentioned already, right? The server is storing the 2 messages with their private data to begin with, and the client stored the bit. Then this is a little cryptic. Maybe they are sharing the parameters of an ECDH public key generation, right? This is elliptic curve Diffie-Hellman. Please raise your hand if you are not familiar with it, and I have a short introduction before showing this. How many people do not know how Diffie-Hellman works?
The one where you establish a secure connection over insecure?
Yeah, in this case, it's less than that. It's a building block for it, but that's right. What's going to happen in this is what this does is it provides a user with basically 2 numbers. One is a private key, and one is a public key. If you share your public key with other agents in a system, they will be able to encode messages in such a way that only you are able to decode it. Okay? It's kind of a deep topic. I don't want to go too far, but I want people who haven't seen it in the past to understand it. So I'm guessing the elliptic curve is basically a group of, as any curve, it's a group of points, right? You may have seen the drawing. It tends to look like this, but it can collapse and have some other shapes. But it's something like this typically. And the advantage it has is it's quite a wildly hard thing to work with, right? It comes from a polynomial. If you look at the equation, it looks harmless, but it's quite complex to work with. And it has an operation which is called point addition on the elliptic curve, and it looks like this. If I want to add this point P and this point Q, I'll do this. I'll trace a line. It's going to intersect the curve again, and this we are going to call minus R, because the point we want is the mirroring of this. It's here. And you may be thinking, that's horrible. What are we going to do with it? We won't do much today. It's a completely different topic. But the important thing is, this is fairly complex to work with. Like, this is very confusing, right? And that's the idea. It's so confusing that it's very hard to know what 2 points game it is. Like, even getting 1 is hard, right? That's the interesting part. These are pairs of numbers, right? In here, in this drawing, since, it's filled, we could say they are continuous, right? So these are real numbers to begin with. What cryptographers always do, a typical technique, is to work on finite cyclical sets of numbers. So what we'll do is we'll grab a fairly large prime number, and we'll only take integers modulo that number. What that will do is to transform this relatively nice thing into something that almost looks thermodynamically complex. Like, we'll get a ton of points this way. And points that were together now are very far away. And it could happen that this operation is involving these 3 points. So how could I get that from here? There's no way. The only way is if I know the pre-images of the operation, right? That's where the security comes from. There's an operation in this set, which is the sum of points, which I've just shown you. And with a ton of effort, you can prove there will never be something akin to multiplication. We have addition, and we'll never get something similar to how multiplication works on regular integers, which, if you want to search for it, there's no rings on the algebraical structure on elliptic curves, right? What that implies is you can build something as a polynomial, and therefore it's very hard to search for solutions, right? When you take your course on mathematical analysis, you learn that when you want to approach a solution at least, you build a polynomial that's similar to the thing you want to analyze, you make it as close as possible, and you get a solution as close as possible. Here you won't be able to do that because there's no multiplication and you can't build polynomials, right? The operation we have, that's what I'm coming to the key now, is multiplying an integer, a number on our chosen group, by a point, right? The operation we will use to get the curves is there's k in zp, right? So integers modulo p. And what we can do is evaluate k by q. What does this mean? That I will be adding q to itself. So q is in the curve, right? Q is in the curve, which we'll call E. E is this thing here. Q plus Q plus Q, k times. Right? This is the product, what we obtain when multiplying a number by a point in the curve. So now that I've said all of this, that we can define the key we want to use in this case. And it's very easy now. What's going to happen is I will have a private key, which is a number. Only a number in ZP, as I've shown you. And what I will do is I'll multiply it, and there's going to be a point in the curve that's G. G is a reference point. We are both users are sharing, right? What I'll do with my private key is, so the private key, let's call it PK, is a number, Q, in ZP, right? And what I'll share with the other user, the public, now let's call it secret key, because the P is in high demand. The secret key is a number. And the public key, PK, is Q multiplied by the point G, which is a point in the curve, which looks like two integers in a pair, right? And it might look simple, but it's very hard to figure out what point has been used, because if we look at what happened when I created this, there was all of these points distributed in an extremely complex fashion, right? And I've done something like this, from this to this to this to this. That's how it behaves. And you can, and the numbers are very big, right? We don't use 2. We want a very big prime number or something like that. So what happens is it's extremely chaotic and it's very hard to figure out. We call it a discrete logarithm problem because similar to how logarithm works with exponentiation, right? We want to find the pre-image of an iterated operation, which is highly complex, right? So what I will share is this. From Q by G, it's very hard to obtain Q again, right? And what the other user will do is, typically to encode something for me, is they will choose a third integer number and multiply this again. From that, they'll grab the first coordinate, which is a number, and with that number, they will generate a mask, which is a series of zeros and ones, which will be applied to whatever we want to encode with XOR operation. So they will change some bits. They will scramble some bits. And the magic of that is if they send us the number they've chosen, let's call it, it's a nonce, and it's, let's call it R in ZP. They will use this, R by Q by Z, right? And if they share with us R by Z, which again is hard to figure out for a third party, right? ZP, no, R by G. We can build on our own R by Q by G, and we'll arrive to the same key. That's what we'll use here. So that's, in a glimpse, how asymmetrical key generation works when you want to use elliptic curves. If anybody wants to discuss this later with me, we can see it in more depth. Do you have any? So what we care about now is will there be two integers, which will be shared, but they will be hidden by using this point G. What we'll send is the product by G, and that will make it pretty hard for a third party to figure out what's happening. That's what we'll use to build our Oblivious Transfer. We've agreed on the parameters we need to use for public key generation. And both members of the communication are choosing a secret key, NSK, CSK, okay? And storing it, of course. The first one that's gonna share their public key is the server. This is the operation here. They evaluate elliptic, curve, diffie, Hellman using their secret key and the point G, and they store their public key, and they share it with the client. Okay, so the client has obtained a public key that they know the server and only the server can decipher, assuming finding discrete logarithm, which in this case is pre-image of multiplication of points in the elliptic curve, is hard, which it is. That's what will give us protection here. The next step is the step in which the choosing happens. What will happen? The client has a, let's say, a function of keys. The client will create a new public key. It's gonna be based on the public key he received from the server, and in how they build it will be encoded what they've chosen. They can, so that's why I'm writing n public key of 0 and n public key of 1. They can only share 1 with the server. The server will only accept 1, so that's when they choose. And for now, we'll say that if they want to pick the first message, their public key is going to be composed of their private key multiplied by the point G, which is the vanilla case I have shown to you. But if they want to choose the second message, it's going to be salted with this. It's going to be the server's public key plus the client's secret key by G. So this element is added, okay? They store both, they choose, and they send one to the server. Which one? The one that belongs to the bit B that was committed before, right? So they will only use one, and it's the one of the chosen bit. That's how it acts. The moment in which the choosing happens is when I decide which one of these two to use, and I send it. I also store, of course, the private key, KB, that allows me to decipher what's been encoded with this key, okay? And then what will happen is the server who received this key, this NPK evaluated by the bit B. So the server can't know how you build your key. The server received an ugly number, right? An ugly point in the curve, sorry. So they cannot know anything. They don't know how you built it. What they'll do is they'll use it to encode both messages. But in this fashion, they will use a C S key by MPK for 1, and this other factor for the K1. So what's going to happen is I receive, sorry, not me, the client will receive two messages, M0 and M1. They are encoded with different keys, one with K0 and one with K1, and given the way we've built the keys, we only know how to decipher one of them, and only one. I show that in a second. But before going back to the calculations, what happens in the end is the client receives the two pairs, and the one that is coincident with the bit B can be decrypted with this private key. This is the private key that is shared between the server and the client, but the server doesn't know which one it is. Let's look why this works. Let's look at why this works. So what I'll do is I'll just go through the 4 cases. There's 2 that should work, which are I choose with bit 0 and I deciphered message 0. I choose bit 1 and I deciphered bit 1. So that's one part of the algorithm. The other is that I can't decipher message 0 if I choose bit 1, and I can't decipher message 1 if I choose bit 0. So the first thing we need to do is to look again at the definitions. So my private key has 2 possible values depending on which bit I've used. And remember again, I sent only one to the server, so I can't use both. The server used only one as the preimage when they created the final public key with which they encoded the messages. That's the warranty of the server. I only sent one of these. It can either be my secret key multiplied by G. No, sorry, the server, see, yeah, fine. This, my secret key by G, or the server's public key plus my secret key by G. And let's see what happens. So KB, the key that will decipher this is built this way. I multiply the server's private key, public key by my private key, secret key, and obtain this thing. That's going to cancel everything in a second. Let's look at the case in which the message is 0. In this case, let's look at case 0, that the key that the server used is ZSK by MPK0, because I sent this one. If I replace it by its value, I get this. So it's the product of CSK and SKG, and that's exactly the value of KB. Therefore, this works. It's only cancellation of numbers, nothing fancy. Like, again, this is all the chaos, but multiplying this by numbers, right, what we are doing is multiplying the point G by two successive numbers, right? And the part in which the integers are multiplied, it's fairly easy. That's what's happening here. There's no elliptic curve. This is product, right? So it follows the rules you'll expect. Then if B is 1, so this is not any much fancy mathematics, right? I know that it might look confusing, but it's numbers, like it's integers. So the same, I had this key, right? If I replace with the value of MPK1 now, because I chose the bit 1, it turns into this, and it conveniently cancels out, and I get again the key KB that I need to decipher the message because it's the one that the server used. Therefore, it works when I choose bit 1. Now, in the crossed cases, both are mostly the same. This is slightly prettier because there's no additions. If I want to decipher the message that I didn't choose, like my bit is 1, but the message 0 is encoded with the key 0. Let's try to evaluate with what we have, and we can only get this. And this is not case 0. It has an extra element, and it requires the server's secret key, and I don't have that one. That's why it's called secret. Therefore, I can't get it. Now we have another intuition for a simulation. We won't do it in detail, but it's fairly evident anyways. Like, if I wanted to vulnerate this algorithm, I would need to figure out the pre-image of an elliptic curve product. And I can't do that. Again, why? Mainly because it's assumed hard, right? That's how this works. It is hard, but it is assumed hard. So if we trust that, we also trust this algorithm. If we want to simulate it, we use random data, and we arrive to the fact that if I have the trace, what I need to do to get information is get a discrete logarithm, which is pretty hard, almost as hard as figuring something at random. And that's why this protocol is secure. Do I still have time to go on, or?
Yeah, you're being long. Yeah, like perhaps because the tsunami lecture is starting soon. I don't know. How long have you been?
Well, I can.
Also later, no?
What? Sorry.
We started also later your lecture. No?
Yeah. What I have is I have two further algorithms, which should be faster, I guess. So I take 10 minutes. Is that fine? Okay. Okay, do you care about this? Otherwise, we can go directly to the pairings. I like pairings better, to be honest, but this is what I can teach.
We will have more lectures with you, I hope.
Okay, that would be great. So let's have at least a superficial look, because something I like about this is you can reuse it as a cryptographical building block to get other stuff, the same way we are consuming this already. This one is a little nasty, to be honest, so we'll leave this one for another day. And we'll one for the other. We have this pretty meme anyways, which is less obscure, so you can see it from afar. And this we'll skip for now, which is a pseudo randomness, because it requires some theory, and it's going to be slower to teach. So we'll go to this other problem. This is,
Just give us just the objective. The objective.
yeah, the previous one, random, I think it's Spanish, so I need to check for the name. Random Oblivious Transfer. In that case, and there's in the material, and we might have time other day to look at it.
One of the two, you don't know which.
In random Oblivious Transfer, you are generating noise together. So it's quite interesting and useful. There's this family of functions, which is called pseudo random functions. And what they do is, if you evaluate this pseudo random function over a set of numbers you know, but the other people doesn't, it's going to look as noise, as if you had just grabbed noise, like white noise from the TV. Even though it is deterministic. For you, you know how to generate it, and you can repeat it as many times as you want. That's how we get randomness inside of computers, which are not random devices, right?
Or to get a ceremony of creation random numbers, right?
Yeah, you could do a ceremony with this also. Like in the ceremony, the numbers, you need to feed a random number. One way would be to use this. And I'm guessing an alternative way of designing a ceremony, which is not needed due to the social engineering in the ceremony, would be if random pairs of users would use this function. No, it's fine. What we'll see is similar. It's another oblivious evaluation, in this case of a linear function, which I believe is faster to teach. Now our numbers, the private inputs of both parties need to belong into a ring. Why do they need to belong into a ring? Because we are going to evaluate a polynomial. It's a humble polynomial, a linear function, but in the end it is a polynomial. Party 1 holds a value A, and party 2 holds a value B. What we'll do is a variety called M2A, multiplication to addition. What this means is, also from the setup, we are in a ring, and elements in this ring can be encoded with, at most, raw bits. So they have a fixed length we know, which we've been using beforehand, but again, in this paper, they were more clear about the requisite. The parties want to obtain X and I fulfilling this condition. So they know A and B. They want to evaluate the product of those two numbers, but what they'll do is they'll obtain auxiliary values that are equivalent to this product when added together. So I have A, you have B. I don't want to give you A, you don't want to give me B. So what we'll do is to create X and Y, and they have the property that their addition is equivalent to the product between A and B. Again, without leaking any private data. If you look at this, if we use the notation I've been using throughout the slides, U1 has a secret input A, and when they evaluate, they do F1 of A is X, and user 2 has private input B, and the function will provide them with Y. This is symmetrical. They get similar stuff, and they also input similar stuff. We could evaluate a regular linear function with this by just, conveniently moving elements around. This looks extremely ugly because, it has the shape of a linear function, but the names are wrong. Sorry about that, but I guess you can change names if you want, and you are evaluating a linear function now. In this case,
There is no inverse. I mean, if they get the product and they know their input, they can recover the other side. There's no inverse or what?
let me think about what they'll get.
I don't give you my A, but then I find out the product AB. I have the A, I divide, I get the B.
Yeah, that's true. I should think about it. But let's say we are in G, so we now can hide it in a point, for example. So we'll do this now with the numbers instead of sharing it. Then it will be hard.
So it's not a ring?
What? No, we A and B belong into a ring, but we can share it with another strategy, I guess. Or we could just not share X and Y, and I guess use it in another way. I should think about it, but what's true is if I don't send you what I obtained, right? If I don't send it to you, if I don't send you X, it's still true that you can't get it. So this works. That I will show to you. I will get, with my A, I will get X. If I don't send it to you, you learned nothing. If I send it to you, you have learned. I should see why this is useful, really. Again, like as with Oblivious Transfer, these are highly situational algorithms. You are right. If I send you X, you might get everything. So we need to think about it. But it's still true that we can turn a product into a sum, right? And we still, if we exchange the secrets, as you said, we are revealing them. And it works this way. The server, the users could change roles in this one. The server will select a random set of elements, exactly one for each bit required, so it's from 0 to ρ minus 1. They will select bits, numbers at random from the ring. And we will also consider the binary encoding of every element here. So these are the binary ciphers. Each one of these is 0 or 1. And these form a binary decomposition. We can recover the number as we did in the primary school by adding, 2 to the power of the index for each one and adding everything together. We should start by 0, like this, not by 1, by the way. And the server will create a set of pairs of messages, which is this fat t. Fat t is vector. Each one has 2 messages, and they look like this. The first is one of the random elements I've selected, and the second is one of the random elements by the number b. This is not the decomposition, it's the whole number b. So 2 power j plus one of the randoms, 2, which makes them blinded again, right? They are hidden by these random additions. Again, only the messages indexed as 1 contain information about the server's private input, which is the number b. The client holds a, and they will also use the binary decomposition of a, which I wrote this way, which is a little confusing. It should be starting 0 and end in ρ minus 1, because the powers look prettier that way. But basically, this is, again, if the number a is 1, 0, 0, 1, this is going to be a 1, a 0, a 0, and a 1. That's it. And they will exchange stuff using Oblivious Transfer. In this Oblivious Transfer, the roles are fixed. The owner of A will use every bit of A as a selecting bit. And the owner of B, the server, I called it in this case, even though this is symmetric, will share the messages they've generated. So in each round, the guy I called the client will obtain one of those T's, either T0 or T1. In the end, they will both evaluate stuff. The client will evaluate the sum of the messages he obtained, and the server will evaluate the sum of the randoms he generated. Let's look at how this works. There's an intuition first, then a demonstration. The intuition is that if we look at the product A by B, let's replace A by its, as I said, by its, this is wrong, this should be a 0. I'll correct it later. But this is the binary decomposition, right? I'm looking at all of the ciphers in the number A, which are either 0 or 1, and elevating by the powers of 2, from 0 to ρ minus 1. And here, in the product, I can replace it. So A by B is like this sum by B. Now I will distribute B, and I will separate the values this way. This is all the indices for which the cipher in A is a 1, no, a 0. And this is all the indices for which it's a 1, right? I separate it this way. These will stay as they are. Now I know there's a 1 here. So this is 1 by B by 2j. And this is a 0, so I can omit it. And in the end, I only needed some of the elements. Can you see? So even though I did Oblivious Transfer, and I didn't get all of the ciphers in the number B, I got some of them. I got the ones I need, and just the ones I need. That's how the demonstration is going to work. So this is demonstration. What we'll do is we'll write A in this way, and we'll rewrite the messages. So all the T0s in the end are just one of these random SJs. But this is the same as saying this is Sj plus 0. So let's add this here for free. Sj is here, and this is a product by 0, so this is still a 0. And so I can write this way for free as long as the cipher is 0. If AY is 0, this cancels out and SJ is T0, which is true. In the other case, it already looks as we want, mostly. It's this thing, 2 by a power by b plus the factor. But again, I can add a 1 for free here, and it's going to be the same. But this one is AI, because in this case, the bit is 1. So I can have the same expression for both of them. They both look like this. What this implies is that if I add all the messages together, like this, I'm actually doing this. And if you see this, this is the exact evaluation of the function. So this is rebuilding the value A. And this proves that what I wanted to happen is happening. If I look at x plus y, this is the sum of the messages the client obtained plus the sum of the randoms the server kept. If I add them together and replace by the expression I obtained before, I get this, which already looks a lot like the evaluation I want. The randoms will cancel, and I will get this. This is the binary decomposition of A, finally correctly written. I'm happy. My PDF can think while I speak. So what's happening here is I'm getting A. This is every bit composing A by the power of 2 that defines it. So this addition will give me A, and I got A by B. What I got is I privately generated a pair of elements, a new pair of elements, that when added together give me the same result as the product. As our colleague here has...
I think I get it. The client has A, the server has B, but the third party gets AB.
Yeah, that's what TLS Notary does. You send it separately to... Yeah, and that's why, because...
Not to each other.
Yeah, because TLS Notary will mediate in the handshake. And that's what's going to happen. You're right. And just to close it, you will have also, this is the algorithm, which I explained with words. This is the schematic. I won't go into detail on it unless somebody has a question.
The verifier, sorry, the third party, the server, no, the third party can be the verifier.
But in this case, it's not as complex as in zero-knowledge proofs. Like, these are very immediate. The only thing they need to do is to do 2 arithmetical operations, a product and a sum. So, yeah.
Then this G
Yes.
is related to the garbled circuit for TLS Notary? No.
Not necessarily. Like, the garbled secret that does not require necessarily a point in the elliptic curve. It will encode the lines in the circuit, but it can use way less complex cryptography to get that done. It can be lighter. So you can use it, but it's not advised.
Because these garbled circuits, like, it's a step for the Oblivious Transfer, right?
Before?
Setup.
Yeah. But again, the fundamental requisite is less. Does anybody else have a question?
Are you going to be around?
Yeah, I'll be around. I'll be around.
Also, we will have Octavio again here. Like, it will not be like the last lesson. I think should continue on the, or perhaps we can have a session about this, like more practical, of perhaps Q&A about this.
Yeah, of course. And you can write to me or ask to me here whenever you want, except now because another class will be happening.
Yes.
I'm in the Discord, yeah, whatever you want. Thanks a lot for using the computer. Thanks.